Okay, so that this theorem has an immediate corollary. And in this corollary, we're going to make use of a well-known fact from multivariable calculus that polynomials in the real plane are continuous. Now, this is something of a cop-out for me because I don't like to use a fact without first proving it. But in the next two lectures, we're going to study metric spaces, and the proof that a polynomial is continuous in the real plane is especially easy in the context of metric spaces. So we will prove that, but for now we're going to accept it as a fact, a well-known fact from multivariable calculus, that polynomials are continuous. So let f and g be real measurable functions in the space X. Then the sum and product of those functions are measurable. Okay, so we're going to make use of the previous theorem. So we're going to define the function phi, which was the map from the real plane into, this time we choose for that second topological space to be the real line, and we'll define, let phi be defined by phi of x, xy, takes as an argument the ordered pair, is the sum x plus y. Then this function phi is continuous as it is a polynomial in the real plane. And so the function h, which again is defined as phi of f of x, g of x, which is, by the definition of phi, f of x plus g of x, by the previous theorem, h is measurable. And so the sum of the functions f and g, where f and g are real measurable functions in x, are measurable. So we need to make a similar definition for the product. So let big phi of x and y, well, again, big phi, the map from the real plane into the real line, be defined by phi of xy, x and y, is the product of x and y. Then big phi is continuous, once again, as it is a polynomial in the real plane. And so the function h, which again is, in this case, big phi of f of x and g of x as arguments, which is the product now, this function h is measurable by the previous theorem. Okay, so a nice thing to know is that if we have any two real measurable functions in x, then their sum and product are also measurable. Okay, new theorem. Let script f be any collection of subsets of a set X, then there exists a smallest sigma algebra, which we'll call script M star in X, such that this sigma algebra such that the collection script F is a subset of this sigma algebra. So we need to make rigorous what we mean by smallest. In mathematics, when we say smallest, we mean the most exclusive set, and so that is the intersection, and so that's how we're going to prove this. So let the set omega be the set of all sigma algebras in X, such that this family of subsets is a subset of that sigma algebra. Now this set, as we have defined it, is not empty. Omega is not empty, as the power set of X is one such sigma algebra. So let this smallest sigma algebra, or what we shall prove is the smallest, the sigma algebra star, be the intersection of all sigma algebras in this set omega. Then, as it is the intersection that contains of sigma algebras that contain the family of sets script F, then this family of sets script F is a subset of this sigma algebra, and this sigma algebra as an intersection is a subset of all the other sigma algebras that are in the set omega. And so this sigma algebra star is the smallest. Sigma algebra that contains the collection script F. All right. Okay, so now we're ready to look at a sigma algebra that is very closely related to a topology because it is in essence generated by a topology. Let X be a topological space. The Borel sigma algebra is the smallest sigma algebra, which will give the symbol a script letter B, such that every open set in the topology on X, or every open set in X, belongs to this sigma algebra. Now this sigma algebra does exist by the previous theorem. There is a smallest sigma algebra, the intersection of all such algebras that contain open sets in X. So the Borel sigma algebra is the smallest sigma algebra that contains every open set in X. The members of this algebra are called the Borel sets of the space X. All right, so one thing to notice immediately is that as this algebra will contain, or does contain, the complement of every open set in the space X. It is also the smallest sigma algebra it is also the smallest sigma algebra such that all closed sets in X belong to the algebra. All right. Now there are two classes of sets that are very useful. Two types of Borel sets of a given space X. F sigma sets are countable unions of closed sets, and G delta sets are countable intersections of open sets. Now the names of these sets are easy to remember if you associate them with their origin. The F sigma sets are named for two components, both French words. The F stands for fermé, which means closed, and the sigma stands for sum, which means union. The G delta sets, the G stands for Gabet, which roughly translates to neighborhood. And the delta stands for Durchschnitt, which translates to intersection. Okay, both of these were named by Hausdorff. Okay, another important thing to notice is I'll let script B be a Borel algebra, Borel sigma algebra in the space X. Then every continuous map F from the space X into the space Y, where Y is any topology, is a measurable function, and we call it Borel measurable. And this is true since for every open set V in Y, the inverse image of that open set is open in the space X, as the function f is continuous, and as it is an open set in X, it is therefore a Borel set. of the space X. All right? So next we have a very useful and interesting theorem. Let script M be a sigma algebra in the space X. Let space Y be a topological space. And let F be a map from the measurable space X into the topological space Y. If the collection omega is the collection of subsets E of the space Y, such that the inverse image of that set E is measurable in X, or is a measurable set in X, then this collection, omega, is a sigma algebra in the space Y. 2. If the function f is measurable, and the set E is a Borel set of the space Y, then automatically the inverse image of that Borel set in Y is in the sigma algebra in X. All right, so the first statement says that if we have a collection of subsets of Y such that its inverse image under any map from the the measurable space X into the topological space Y is in the sigma algebra in X, then that collection is itself a sigma algebra in the space Y. So we'll first prove that statement. So first we notice that the entire set Y is in the collection omega, since the inverse image of the set Y is the entire set X, which is always in the sigma algebra. Second part of the definition, let the set E be in the set omega. Then the inverse image of that set is a measurable set in X. And as this is a measurable set, its complement is also measurable. Now, since the complement of the inverse image of the set E is the same as the inverse image of the complement of E in Y, we see that the inverse image of this complement is a measurable set, and so this is in the collection omega. And so we have that if a given set E is in set omega, then its complement is in the collection omega. All right? So let the sets A sub n be in the collection omega for every index n countable. Then the inverse image of A sub n is in the sigma algebra in X for every index n. And so the countable union of these inverse images is also in the sigma algebra in X. Now, since the union of inverse images of a collection of sets is the same as the inverse image of the union of those sets, we see that the union of these sets is in the set omega, since its inverse image is a measurable set. And so we have the condition that if a countable collection of sets is in the collection omega, then the countable union of those sets is in the collection omega. And so by definition, the collection omega is a sigma algebra in the space Y. All right? Second statement of the theorem is that if we have a Borel set in the set Y, then its inverse image is automatically in the sigma algebra or in the space X if the function f is measurable. So let the function f from the space X into the space Y be measurable. Now, any Borel set in the space Y is going to be composed or generated by the open sets in Y. So every open set is a Borel set. Any countable union of open sets is a Borel set. Now, the complement of every open set is also a Borel set, so the union of those is also a Borel set. So for the proof of this theorem, it will suffice to show that the inverse image of an F sigma set is in the sigma algebra in X. So it suffices to show that the inverse image of an F sigma set is measurable, or is a measurable set in X. All right? So let C sub n be closed in the space Y for every index n. Then the inverse image, then the complement of the set C sub n in Y is open in the space Y for every index n. And so the inverse image of open sets is in the sigma algebra in X for every index n. And this is true since the map F is measurable. So since F inverse of the complement of C sub n in Y is the same as the complement in X of the inverse image of C sub n, we have that the complement of the inverse image of closed sets is in the sigma algebra in X for every index n. So as this is a measurable set in X, its complement is a measurable set in X. And so we have that the inverse image of closed sets is in the sigma algebra in X, again for every index n. So as each of these sets is in the sigma algebra, we have that the union of these sets, the countable union of these sets, is also in the sigma algebra on X, or in X. So since the union of inverse images is the same as the inverse image of the union, notice that the union of closed sets is an F sigma set. We have that the inverse image of an F sigma set of Y is in the algebra in X, sigma algebra in X.